A huge thanks to Brian for sponsoring this video. To be honest guys, I had a pretty awful day up until now. It was terrible. Everything that could possibly wrong went wrong at my workshop. Just was not a fun. I went back early from my shop. Wasn't good. I think my day is pretty much ruined, but I still thought to myself, Jent, you gotta record a video today because people requested an ultimate mathematical functions tier list the most. And this is what we're going to take a look at today. Mathematical functions sorted in an arbitrarily instrumented tier list. But if you feel like making my day a tiny little better, why not make sure to check out my newest video over on Flammy's Wood. Started a new series linked in the description or the info box or wherever. And I think we shouldn't waste any more time. Let's dive the fuck in. So, mathematical functions tier list. Functions maker, tier list maker. This is what I called it with a very, very nice description. WDQEFA. You can find the link to the tier list under in the description to sort them for yourself if you wish. And I think we should start off with some of the more basic ones. There are basically three types of functions that you're going to find in here. Functions you learn at school, special functions that a bunch of people know about, and then very special functions which some of you may have never heard about, but I thought might deserve a spot here in this tier list. We got a very nice rank today, or very nice ranks. They are C, HU, N, GU and S, with S being the best rank, and we're going to sort it from downwards to upwards. And we're going to start off with an absolute classic. It's the thing that pops up everywhere in number theory and the like, algebra. It's the so-called identity. If you use the identity on something in composition, for example, it's just going to spit out the thing in and of itself. If you compose the identity with a function, it's just going to be the function in and of itself. What could the identity function be? Well, it just maps some value x to basically x once again. This is what you do. Identity of x, and it's a pure classic. I just love proofs that involve the identity. Proof that the identity is unique, for example. Proof that there's only one identity in the real numbers. It's the number one, at least in terms of multiplication, for example. And it's just a very fun function, and I really like it. And if you do like it too, then make sure to put it here in the GU rank, because this is one after the S. There are better functions out there, but it's a lot of function. It's a cool function to work with. So the identity goes into the GU rank. Now let us step our game up a tiny little bit. Why not take a look at the next thing that could basically come after the identity function? They are the constant functions. Pure classic. I have chosen one random, arbitrary, totally not planned constant function, namely the function y is equal to 69. Just randomly chosen. There's really no second thought behind it. It's just number 69. It looks kind of nice, but it's nothing special, to be honest. What's so cool about the constant function? Well, the constant function is constant. I mean, yes. And because it's so special and it doesn't change when you put some values up its r's, I'm going to give the constant function a solid worst rank. I just can't think of a good argument for why the constant function could be cool. If you find an argument for it, then make sure to post some comments down there in the description. The constant function isn't very cool, but do you know what is cool? The contents of today's sponsor Brian, who are kind enough to sponsor yet another video here on this channel. Now, functions are prominently featured over on Brian. If you haven't heard about it before, no worries, I'm going to explain it a little bit to you. Brian is your source for some of the best online learning content out there on the internet. With their interactive learning concept, it's a once-in-a-lifetime chance for you to learn something in a very intuitive fashion, graphically. Functions being portrayed by their graphs. You can play around with those graphs by varying the parameters, for example, inside of the constant function. There are no parameters to vary in the constant function, but you probably get the point. You can set the constant function at being just c, and then you can vary the c value and see what it looks like once you vary this very parameter c. Yeah, that was a weird sentence, vary the very parameter c. But yeah, Brilliant does this all over the place. If you take a look at their website, all of their courses are being just backed by all of those graphics and the visuals that you can play around with. Over the years, especially as a teacher at a high school, I learned the hard way that students don't like abstract things. Totally not. They don't enjoy this. But what they really like are visuals, things that they can grasp, that they can see, that they can touch with their own two hands. In mathematics, if you talk about 3D models, it doesn't work out nicely for the students if you draw them at a chalkboard, for example. What you need to do is you need to take a model of a geometric figure and give it to them, let them explore. Or in the case of Brilliant, take a look at their website, take a look at the geometry course and take their graphics and rotate them in 3D space around with this 2D projection appearing on your screen. Especially in the geometry section, they do a great job at visualizing triangles and the like. So if you're curious about their course concept, why not make sure to check out link at the top of the description, brilliant.org/FlammyMaths. With it, you're going to get free access to a big portion of Brilliant already, so you can try it out, at least for free a tiny little bit. But more importantly, the first 20 people to actually make use of the link get 20% off an annual Brilliant subscription, which is a freaking great deal considering how much content they already have available on their website and how much content they are adding on a regular basis. So definitely make sure to check it out and support the channel this way. And now we are going to go back to the, no, not meme review, it's a tier list. This day sucks, I told you so. Now 69 has been put in the worst rank possible. But there is one constant function that came to my mind while creating this tier list, which is really something special, and just because of one very cool fact, namely the constant function 0, the zero function. What is special about the zero function? Why did I add it here? If you think to the zeros of a function, and especially the zero of the constant zero function, how many zeros does it have? I mean, it lies exactly on the x-axis, cutting it at infinitely many points. You might think that with those arguments it has infinitely many zeros, but actually most mathematicians claim that it has negative infinity many zeros, the zero function. So why is it that way? So just think about it as being a polynomial. X to the first power has at most one real zero. Polynomials of degree 2 have at most 2 real zeros. Now what about 0? Just think of it as a limit, and I think this is the standard argument that mathematicians go with. 0 is the same as 1 over infinity, okay, in the limit. Infinity could be the same as x to the infinitive power. So this is 1 over x to the infinitive power, you could say. So x to the negative infinitive power. And I think you can see the point. By just interpreting it as a polynomial in the limit, you're going to get that it has negative infinity many, negative infinite, however you pronounce it, I don't care, many zeros. And I think this is a cool fact, and for this it deserves the middle rank, N. Now, next up we are going to go over to a bunch of classics. Speaking of the identity, the identity is x to the first power. This is what you call a polynomial. And we're going to take a look next at polynomials of degree N. Now, polynomials are pure classics. They are the whole reason why abstract algebra basically came to be. We wanted to find out the zeros of polynomials. And yeah, just because of this reason and everything that sparked this small idea and everything that came out of it over the years, I just have to give this pure classic an S rank. Polynomials are of interest in each and every field, and if you expand the idea of polynomials into infinitely many terms summed up, so series expansions, it gets even more interesting, generating functions and the like. And this is why they are definitely an S rank. You can disagree with me, but I don't think you will. They're just pure classics, and they are the main spot of each and every school career, you could say high school career. Taking a look at polynomials, reconstructing them, and just observing what they do, giving you a perspective into eventually higher mathematics at some point. Now, what would come next at schools after polynomials? After polynomials, you are probably going to take a look at root functions next, and this is what we got next. You're going to start off with the square root, then the cube root, and the like, and maybe some funky stuff like the fifth root of blah 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 to the third power. Well, this is weird. Now, roots are cool, but they can also fuck you up pretty bad once you get into negative numbers as the arguments, or just in general the solution to root or non-linear equations, because then you're going to go into the complex realm. And then you have to deal with branch cuts and all this crazy stuff. And I think just for this, and because they are annoying as fuck, they deserve one of the worst ranks possible. Now we filled each and every rank up for now. And after the root, what could logically come next? The next thing that comes to my mind is the logarithm. Now here we got a logarithm. And I hope many of you are really triggered by the formatting. I made sure that they are stretched and everything such that it looks extremely ugly. Now the logarithm. The logarithm by the same arguments can have a lot of branch cuts, and if you're not careful you're going to get negative arguments and maybe a negative base and the like, and this just turns into a whole new beast. Complex anal doesn't make it any more nice to deal with. But cool thing about logarithms is you can always say, hey, I just gotta take a look at the principal branch and then all my problems are gone, whoosh. But in general the logarithm is just cool. It's not like this shitty root function. The logarithm is cool in the sense that you can turn multiplication into addition, for example. And this is really cool. You can use the logarithm to take a look at infinite products, turning them into infinite series, for example, making it easier for us to grasp and to work with. Logarithms are continuous in their domain, meaning you can track the limit to the inside, and so on and so forth. Logarithms are really cool, especially the natural log. And just because they are so seriously cool, they deserve a G rank. And they are ubiquitous. You're using them all the time. They are everywhere. I just love logarithms, and you should love them too. Now what about the polar opposite of the logarithm, the so-called exponential function? To trigger some of you, I used exp, and then I used var theta in here. That's some ugly notation, but in some cases exp is actually better than e to the something. Now the exponential function, in my opinion, is totally overhyped, but it's not like pi or phi or e overhyped. E is just exponential function, it's one, but never mind. It's a good thing. The exponential function is a very good thing, and it helps in integration. It helps turning other exponentials like 2 to the x power into just natural form, basically e to the something, using the logarithm too. And it's just fun to use. The derivative is easy, the integration in a normal case is very easy to do, getting a lot of elementary functions out, apart from a few uncountably many exceptions like e to the negative x squared. But they're also fun to integrate. I love when the exponential function pops up in integrals. And I think since it's a pure classic, and even though it's overhyped, it really has its purpose. It deserves an S rank. Just like the polynomials. It's a bit better than logarithm. It's just everywhere. And people love it, and you should love it too. The exponential function is overhyped for a reason. Just like Death Note as an anime. It's overhyped, but for a reason. It's a really good anime. And I say this after having watched over 900 animes. So you should believe in my opinion. There was my doorbell. Be right back. I'm back. Gosh, I hate when that happens. Now, what could come next after the exponential function? It's probably the other way around at schools. I'm not certain for sure, but going by the university kind of thing. After the exponential function, evaluate at real arguments, we evaluate them at complex arguments, giving us a whole new world called the trigonometric functions. I have put all of the trigonometric functions into one sine of z. Now, trigonometric functions are very useful. They are used in integration a lot, doing trig substitutions. They are used when doing trigonometry, geometry and the like. They pop up everywhere. Right triangle, trigonometric function. You get a polynomial or a rational function integrated, trigonometric substitution. It's just everywhere. They are seriously useful. I love them. And when you put complex arguments into there, it's going to be a lot of fun too. We're going to go into detail more on that in a second. Just because they are so very cool that they deserve a GU rank. Now, speaking of putting complex arguments into the exponential function, if you have e to the ix, you are going to get out cosine of x plus I times the sine of x. This function actually has a name, and not many people know this. This is the so-called cis function, because cosine plus I times sine, cis. And this is basically Euler's formula, and it's extremely useful. You can derive a lot of shit using Euler's formula. And just because we haven't put much into the lowest ranks, it's going to get a C rank. It's extremely useful. I'm using it all the time. I just love using it. It's one of the most useful identities I have ever learned in my whole career, and this is why it deserves the worst rank, because we don't have much up there yet. Now, get away, fly. I hate summer. So many insects everywhere. Next up, talking about the trigonometric functions with complex arguments in there. If you evaluate those and play around with the Euler expressions of those a tiny little bit, you're going to get a whole new class of functions out. They are the so-called hyperbolic functions. And I denote the hyperbolic functions, all of them, with the hyperbolic tangent, tang of z. They are fun to play around with, and they pop up especially in hyperbolic geometry. If you've never done this, it's a lot of fun. You should definitely check it out. It was one of the most fun parts of elementary geometry I did at university. And to be fair, they are not as useful as the trigonometric functions. And because they are not as useful, but basically as cool, I'm only going to give them an N rank. Now, you can't have trigonometric functions or hyperbolic trigonometric functions without talking about their inverses. We had inverses all the time, logarithm and exponentials, polynomials and roots. Now, what about the inverses of the trigonometric and the hyperbolic functions? They are here. Let's start with the inverse cosine. And I'm going to make this quick. They are useful in integration and a lot of other applications. Finding out angles, so using the inverse trigonometric function to find out the angle that you need to get a certain value out. They are highly useful. They are inverse functions. But one thing that is just the best part about all of these is the notation. So many people are getting fucking annoyed about cosine to the -1 power, you could say. And just because it's so much fun. So much fun to annoy purists and all of the other bunch with a lot of horrendous and very confusing notation. It's going to get an S rank. And since the inverse hyperbolic functions are not as cool as the inverse trigonometric functions, they are going to get 1 rank less. I don't even have them in here. If they were here, they would get a GU rank. Now, next up is something that is very close to my heart. We are still not done with the trigonometric functions. They are just a terminologic mess. I'm talking about the so-called verse sign. They don't have a proper use anymore, but I made a Unit Circle 101 video a while back in my Math Snack series. You should definitely check it out. It's amazing. Where I covered those. And they are just so much fun to pronounce. Just take a look at this function, h cover cosine of phi. No, that is theta, right? That's regular theta. And they are just absolutely ridiculous. They are just another way to rewrite trigonometric functions equivalently, just with the addition of a factor of 1/2 or something, a summand of 1/2. And there are not many uses for them, I admit that. And they are pretty shitty, they suck dick, but they are fun to pronounce. And because they are fun in this kind of way, I'm going to give them a T rank. You should look into those versine functions, okay? Versine, like ver and sin. And there are also the the inverse versine functions, and they are equally nice to pronounce. Arc, arc over cosine. Who the fuck comes up with this? So much stuff to write out. And because they are more fun to pronounce than their little regular brothers, I'm going to give them an N rank. That's amazing. Now, we are basically in the realm of more special functions now. And we are not done yet with the trigonometric functions, because there's one function that I also covered here on this channel, which is kind of dear to my heart. I looked into it a tiny little bit, it was a lot of fun to research, and it's the so-called Gudermannian, denoted as GD of, and I was using psi here. Now, how is the Gudermannian cool? In a normal case, what you need are complex arguments inside of the trigonometric functions to turn them into hyperbolic functions. This is the standard way. But the Gudermannian, defined as being just the integral of the secant, if I'm not mistaken, is going to give you a way to transform trigonometric functions into hyperbolic functions by the means of integration without making use of complex arguments. That's a very cool thing to do, and I think this deserves a high spot in the list. C. That was groundbreaking back in the day, and I really appreciate the effort. This is why it gets the worst rank. I really love this one. We just need to fill it up. We need to fill up the worst rank. I'm so sorry, purists. Now, we are finally done with the trig functions. What else do we have left? Now, let us get into some number theoretical things. And the first thing we are going to cover are the so-called floor and ceiling functions, denoted by those funny little brackets here, down here. Now, what I have here is just the floor of pi, which is 3, but I could have just written the floor of 3, it's equivalent. And the floor function, it's a pain in the ass. I mean, in normal case, it has a very easy definition. You are just going to use the next lowest integer to a number. So the floor of 3.2 is 3, for example. But have you ever tried integrating floor functions or exponents of floors or floors in exponents or the like? That's not fun to do. And because they are just making us number theorists and integration experts struggle for hundreds of years, the floor function is going to get into the worst rank. It's terrible. But do you know what is even more terrible? Fractional part. Because the fractional part can be defined as the number in itself minus the floor. Meaning you are going to get a double bitch out. And I can't even put it less than C because it's already in the C rank, the floor, but it sucks equivalently hard. Integrating or differentiation of the floor or the just fractional part is terrible. And I hate it. And this is why it deserves this low of a spot. Now, still number theory. Number theory is fun, and this is why I added 2 functions. It's one being the Euler-Toschian function, phi of n, and the other one being the pi function, which is the prime counting function. Let's start with the prime counting function. If you take pi of 100, for example, it's going to count all the prime numbers less than 100. There are a bunch of those in there. Try it out for yourself. There are not many, you can calculate through those, spitting you out a number. And the graph you are going to get is pretty fairly interesting. It has nice asymptotics coming with it. The asymptotics being that it's asymptotically equal to the logarithmic integral, if I'm not mistaken right now. I haven't done this in a while, but this should be the case. And we got a lot of conjectures out, and a lot of stuff has been proven over the years regarding the prime counting function, especially the asymptotics. And this was groundbreaking back in the day. Riemann was working on it, so many number theorists, and I studied it a tiny little bit too, and it's just absolutely beautiful. And just because the prime counting function relates in integration and the like too, and asymptotics, it just deserves the highest spot. It's just beautiful. Now next up is the Euler-Toschian function, and I don't know the complete definition at the moment. Let me just tell you, it popped up in abstract algebra once in a while, and it was pretty useful when dealing with exponents of big numbers, or very big exponents of numbers in general. And since it's pretty useful, but I don't know the definition right now, I can't give you proper explanations at the moment about this function, so it's going to get into the HE rank. Now, what else do we have left? We got a bunch of special boys. Let us go to the logarithmic integral. I don't have the logarithmic integral in here at the moment, but I kind of have the inverse of it, kind of. I mean, it's not the inverse, it's just introducing a substitution, and then you're going to get the exponential integral out. There's a whole class of exponential integrals of degree n. But what I can tell you is that we know a lot about the exponential integrals, and you get the sine integrals out and the cosine integrals by using Euler's identity and Euler's formula. And it's a lot of fun to play around with, plays a huge role in analytic number theory too. It's pretty dear to my heart. I have studied it a lot, and also the asymptotics, and because it's such a cool function, it deserves a GU rank. Now, pretty similar to the exponential integral is the so-called gamma function. The gamma function is also a construction that basically generalizes the factorial. The factorial being just a discrete value, 2 factorials, 2 times 1, that was a great example. Yeah, the gamma function gives it continuous values, and the gamma function played a huge role in my life up until now. Made so many videos on it, spent so many hours on end working with the gamma function, and if you've watched my channel for a while, you know how much I love it. And because I love it so much, it's going to go into the S rank, obviously. Ow, my hand. Now, gamma function, what else do we have? Which other cool functions? Other cool functions that pop up in number theory are the so-called polylogarithms. They are basically just generalizations of the series expansions of the logarithm. Logarithm has a certain series expansion, and you can generalize this by putting powers into the denominator. And the polylogarithms also play huge roles, and we know a lot about them. We know a lot of special values and approximations and the like, and they are extremely useful. And one special case of the polylogarithms is obviously the regular logarithm and its series expansion, the natural log. And because it's extremely useful, it's a generalization and it's really cool to work with, I'm going to give it a GU rank, just like the regular logarithm. We are in the final stretch, and what else do we have? Before we get to the really special functions, I'm going to cover a bunch of those that I have covered on this channel here already. We are still number theory. Let's take a look at the Riemann's zeta function, and I don't need to say a lot about this, okay? Riemann's conjecture, and just in general how useful it is in the evaluation of integrals and the like, how many insights we gathered over the years when it comes to the Riemann's zeta function. It's just a pleasure to work with. And I also calculated its fractional derivatives, for example. It's so much fun, it's hella fun. It gets an S rank. And equivalently, close to my heart is the Dirichlet-Eta function. I actually like it even more. It's a great little brother. It's the alternating version of the Riemann's zeta function. And it doesn't have the same convergent issues. It converges better than the Riemann's zeta function. I just like to work with it. And I can put it higher than the Riemann's zeta function. If there were an even greater rank than S, I would put it there because my most favorite function ever, but I'm still going to put it here into the S rank. Now next up comes the memes, the meme, the legend, before we get to the Lambert W function, I would like to take a look at the generalization of the Riemann's zeta function, which also includes the Dirichlet-Eta function, for example. It's the so-called Leertranszendent. I have worked with it, I have calculated its fractional derivatives. It's a generalization. It has a lot of uses, but it's not as close to my heart as those two. And the Leertranszendent, because we don't have many in the HU rank, is going to go there. Read into it, it's a lot of fun, it's a generalization. I thought I might put it here because not many people know about the Leertranszendent. It's a multivariable function, but it's great to work with. Now, Lambert W function. What is Lambert W function? If you have a function being defined as x times e to the x, if you want to find out the x value, you are going to apply the Lambert W function, at least on the principal branch, to it, and you are going to get the x value out. It's just a special function that you just need to approximate. Okay, there are only a few special values that we know about that we can deal with, but other than that, it's basically just a function which is there to give you a better approximation of the problem at hand. I have used it in a bunch of videos at times. I'm pretty neutral when it comes to it. It's useful, but it's not a cool quantity that is going to give you a lot of insights into the into basically the solution of such problems. But since we know a lot about it already, we know how to approximate it, we know it's pretty decent series expansion, I'm going to give it a middle rank, an N rank. Now, final stretch. Before we get into the really special ones that some of you probably don't know about, there's one that is also really close to my heart, which is going to go into the S rank immediately. It's the Lagrangian. Come on. Lagrangian. I don't need to say anything more about it. Minimizing problems and just using the Lagrangian is a bliss. And it's my most favorite part of physics ever, and I think it's for a lot of people too, Lagrangian mechanics. And it just deserves a place here because it plays a huge role in differential equations in general. So we need to put it here. It's not just a physics thing, it's a rigorous mathematical thing, and it's great. Now, differential equations, speaking of which, there are a bunch of those. Why is it double here? Why is it twice? Never mind. There are a bunch of solutions to a class of differential equations that we know a lot about at this point. There are things like hypergeometric series, Bessel functions, the elliptic and hyperelliptic series and integrals and the like. They are all just solutions to certain differential equations, and many people probably have never worked with those, but if you were more into physics and solving differential equations, one of those probably popped up and they give you a hell of a time. They are making your computer struggle because they are so computationally hard to do. Bessel function, for example, terrible, but we know a lot about those at this point, and because we know a lot about those, and just because they give you analytic solutions to certain differential equations that you could in a normal case not work with if it weren't for one of those, I'm going to give the Bessel function an N rank and the hypergeometric functions, because I think they are not as useful, a C rank, because we don't have many up there up until now. And then we once again have the hypergeometric function. I'm going to give it an AG rank, and you can choose for yourself which rank it really deserves. And I thank you guys for watching. And if you did enjoy this video, why not make sure to subscribe to the channel? Try out the tier list for yourself. There are a lot of good functions in here. I gotta admit that there was a great list, but it took quite a while to go completely through it. And indeed, I'm in a better mood now. This really helped. It was fun to go through this video, and I sincerely hope you enjoyed it too. And don't forget to check out Flammy's Wood and also my woodworking shop, stamage.eu, for handcrafted products. And up until the next video, I wish you guys a fabulous day. Ciao!